Indianness refers to storage of bytes of multi-byte integers. So we have to be aware of Indianness when programming, for example, programming network hardware, because TCP/IP data packets transmit in big Endian format. But you can see we have a variety here. MIPS Mars on my Windows machine here has little Endian storage, others have big Endian, and ARM, which is your Android device, has a configurable Indianness, also supported by MIPS specification. So I recommend you review the details in this article and in the textbook. Here we have a general template for writing MIPS assembly code. Data directive specifies where the constant and variable definition will go, and text directive specifies where executable assembly instruction can be written. You should be able to find descriptions of different parts of syntax like comments, directives, mnemonics of commands, names of registers, and other parts in this help section of the integrated development environment. In this MIPS tab, we have information about all instructions available in MIPS assembly, also extended instructions, which typically translate to a combination of instructions when we build our programs, also assembly directives, system calls to communicate with the operating environment, for example, printing characters, getting user input, and other parts of MIPS assembly like macro definitions. A simple example of assembly program. An EQV is a directive that defines a constant which is used by the assembler while your program is being built. So here, if you look at the list of syscalls and scroll down, you'll find that you can print integer, print double, and print string, and the requested service constant is found here in this column. So for instance, to print string, I define it as 4, and to exit the program right here, to terminate the execution, the constant is 10. So instead of using these literal values hard-coded somewhere in my program, I tend to give them recognizable constant names. So the next part here is the data directive, where the data segment begins. And we use another directive, ASCII 0, which reserves a sequence of bytes in computer memory, including new line, and also terminate the string with a null character at the end. In front of it we have a label which represents the address of the first byte in computer memory. Again, I recommend that you take a quick look at the list of available directives to familiarize yourself with what you can do here, primarily reserving memory and allocating arrays of variables. Another directive here indicates where the code segment begins. So everything follows here is a set of instructions and system calls. So here we load immediate value of print string code like this. So this really becomes number 4. We load it into register V0. We load address of our message into register A0 and make a system call which will display our text on the screen. Similarly, we specify that we want to exit the program and make a system call which does not return back but terminates the program and stops the execution. I'll close this window and give it a quick try. So simply copy and paste into our coding window here. You can save the program, and then you have to build it, which opens the Messages tab. You can check whether your assembly finished successfully, and then to run the program you can use these buttons to step through the code or to run it in a normal mode. Okay, so here we have our message, hello world, and of course it comes from our memory and is printed by the system call right here.